Hello, welcome to this second tutorial in the tutorial series for MIDAS Gen. This tutorial is about the pin jointed truss analysis using finite element analysis software, MIDAS Gen. So in this particular tutorial we'll be looking at a statically determinate structure of our pin jointed truss, which is the truss shown in the figure here. Let me zoom in. Okay, so basically we have a truss with diagonal members and the inclined top chord and bottom horizontal bottom chord members, and then the total height of the truss is 3 meters. The total length of the truss is 12 meters with 3 bays at 4-meter intervals. We have 2 point loads applied on the structure. So one is a horizontal 6 kilonewton load and the other is a 21 kilonewton vertical load at point C. All the members are at 45 degrees to the horizontal, all the diagonal members basically, and the truss is basically simply supported at ends A and C. So a pin support at A and a roller support at C. And now we will look at the modeling of this structure in MIDAS Gen, and we will find out what are the reactions at ends A and C, and what are the forces in the members, namely these members here, FD, FE, FG and CE, and whether the forces are tensile or compressive in nature we will determine from the finite element analysis. Once the analysis is done, I will also show you the correlation with the hand calculations. So let us begin the modeling of the structure. Okay, so we start with a blank MIDAS Gen window. You can open a new MIDAS Gen window from the start menu or from the desktop. So I'll click on new project and we get a gray screen here from the modeling interface. XY the horizontal axis and Z is the vertical axis. The explanation of all the menus and the different features in the graphical user interface have already been done in tutorial 1, so I will just skip that part for this particular video, and I'll straight away go to setting up the unit systems. So go to tools, unit system, and select kilonewton and meters. Click OK and go to model structure type. Since this is a 2D analysis, so we will change the structure type to XZ plane. Every modeling and all the loads will be applied in the XZ plane only. So click OK. Right, now we go to model structure wizard and beam to generate the bottom chord beam. So here we have 3 bays at 4 meters, so we type 3 at 4 and add, and we initiate the model with some default material and section, so that's 1 and 1 here, and click OK. So we have got a line. Okay, we can display the node numbers and element numbers for this line by clicking on node number here. So we have these nodes, okay, and we can click on element numbers to display the element number, the number of each finite element. Okay, so for now I will just remove the element number display and only show you the node numbers. Okay, so switching back to the front view, that's the front view here. Okay, now I will add some materials and sections to this bridge, to this truss. So model properties, material, add. We can define steel, concrete or user defined. Let's go for user defined in this case. So modulus of elasticity of user defined material that we will select in this example is 200 gigapascals or 2 into 10 to the power 8 kilonewton per meter square. Okay, that's material 1 and click OK, close, then go to model properties section, add a new section, Select DB user tab and select solid rectangle. Give this section a name, section 1, user type, and enter the dimension. So 0.5 meters by 0.5 meters. Now though the drawing suggests that it's just a line, but that's good for the manual calculations, but for any finite element analysis, each and every line element should be associated with a property, otherwise the software won't be able to solve the problem. So that's 0.5 by 0.5 meters. Click OK and close this. Okay, doesn't matter whatever section property you use, as long as this is a statically determinate structure, you will end up with the same results. Okay, now to see what information you have defined in this model, you can go to the works tree and see what all materials and sections you have defined. You can always edit the section dimensions by just right clicking on section and going to properties, and you can change any values that you want to change, or change the shape of the section entirely. Okay, so now I will model the other members. Okay, so let's go back to the PDF drawing and see what are the dimensions. So we have member AB, which is 2 meter higher than point A and somewhere at the midpoint here, and this is 45 degrees, so 2 meters horizontally as well as 2 meters vertically will go up. Okay, so how do we draw it? We use the extrude function in MIDAS Gen. We go to model and go to elements and go to extrude. So using the extrude function, we can generate a line out of a node, out of a point. So we use this particular node as a reference. So select, using the select single option, a cross here appears, and we can just simply click on this node to highlight it. Okay, and type in the equal distance category, type in 2, 0, 2, which is 2 in the x direction, 0 in the y direction, because this is a two-dimensional structure. So y direction is into the plane 0, and 2 meters in the z direction. So remember that this particular box is the Windows sensitive, so if you snap on any part on the screen, it will change the coordinates. So don't move your mouse outside this left column once you have entered the coordinates. So 2, 0, 2, and apply. Okay, click on the front view. Okay, then again this time select this particular node here, and let's go back and see what are the dimensions. So this one is 1 meter high and it has moved 4 meters in the x direction. So we have selected this node and we type in x 4 and 0 y and z is 1 meter and click apply. Okay, next thing, we again select this node and this time we type in 4, 0, -1, apply. Okay, again use the selection option, select this node, and this time we can directly click on measure the distance. So click on this point, this box here, and then click on this node and this node to measure the distance. That's automatically entered, and apply. Okay, so that's the skeleton model. Now we need to input the inner diagonals. So this time we go to model, elements, and create elements. Just to make the view more clear, I will remove the hidden view so that it's a line view now. And now I will click on this green box here. Okay, and once any box is green in MIDAS, you can simply snap on the model view. So I've clicked on this box, and now I'll snap on this point and this point here, then snap on node number 2, node number 6, then snap on node number 6 and node number 3, then snap on node number 3 and node number 7, and then close this. So that's done. That has modeled the skeleton of the bridge. All our elements, members have been modeled. Now we apply some supports to this truss. So we go to model, boundaries, supports. We have a pin support here and a roller support here. A pin support, as we discussed in the last tutorial 1, a pin support allows only allows rotation but restricts the translation in the X and Z direction. So we select TX and TZ and selection tool and highlight node number 1 and apply. So that's the pin support. We remove the TX now because a roller will allow horizontal displacement but will restrict the vertical displacement DZ. So we now select on our node number 4 and select only DZ and apply. So that's the roller. Okay, now the next thing is we make sure that all our joints are pinned, because this is a pin jointed truss and we have connected them rigidly using beam elements. Now there are different types of finite elements. You can use beam elements, you can use some elements are called bar elements. So they have different characteristics because they allow certain kind of they allow certain degrees of freedom only. So in our case we have used beam elements, and beam elements allow only allow 6 degrees of freedom, that is rotation and translation. I'll just save this model. So I'll just create a name for this, example 2, save. Okay, now for a pin jointed truss, every joint in the model should be pinned. A pin joint means it should allow rotation everywhere. So it will only restrict the displacement, but it will allow rotation everywhere. So you will not get any moments, any bending moments in anywhere in the model. You will get only axial forces, tension or compression in the members. So we need to make sure that we have provided such kind of joints everywhere. So we call in finite element software, we call them as releases. So we go to model, boundaries and select beam end releases. So basically in the beam end releases, what we are doing is we are releasing the moments, or we are allowing the rotations at all the elements here. So we select all the elements by clicking on select all. Okay, and we make them as pinned, which means all these members will have both their ends pinned. So for example, if you take this member for instance, pinned will mean that this particular end and that end will be pinned. Two ends of an element in MIDAS chain are referred to as I and J, as you can see here, I node and J node, which means if this is the I node and this is the J node, and pin will release the moments at both the ends. So we click apply and you can see pin joints are generated at the ends of the beams. Close this, and now we are ready to apply some loads on the structure. So to apply the loads, we create a name first. We go to loads, static load case, and give this a name, say P, and type is user defined add. Okay, now let me go back to the PDF document and see what are the values of the loads. So we have a 21 kilonewton vertical load and a 6 kilonewton horizontal load. Going back to the software, go to loads, nodal loads. So any type of concentrated force or point load is applied using the nodal load option. First we'll apply the vertical load, so that's minus 21 kilonewton Fz, minus because it's in the downward direction. Select this particular node and click apply. Then we make Fz 0 and enter Fx as 6 kilonewton, and this time we select the node number 7 here and apply. Okay, and close this. To see the values, whether we have applied it correctly or not, we can just right click on the works tree and display. Okay, so that's correctly applied, then undisplay. Okay, so now the model is ready, all the supports and loads have been applied. We can now analyze this model. So go back to analysis and perform analysis. Okay, now once you have performed the analysis, you will find that there are some warning messages displayed. These warning messages are appearing at most of the nodes here. Okay, so why these warning messages appear? Because the software is telling you that this kind of a pin jointed structure is unstable, may be unstable. Now in our case, all the loads are applied directly at the joints, which means you are not experiencing any movement at the joint, so that's why it is okay. The warnings are not a problem. But in case if you have a 3D structure where you have all kinds of loads applied, and if you then apply pin joints to all the supports or all your joints, then you will have a kind of an unstable structure, or a mechanism will be generated and the structure will lose equilibrium and it may fail. So in that case the analysis will not run and error messages will be displayed. But in our case, since all the loads are in XZ plane, all the loads are directly applied at the joints, so this is not a problem. So we can ignore the warning messages and we can start looking at the results. So we are in the logged mode now, or also called the post-processing mode. If you want to go back and edit anything, you have to use the unlocked or pre-processing mode. So we go to results and reactions, select reactions, forces and moments, select Fx, Yz to display both horizontal and vertical forces, reactions. Click on values and select the number of decimal points, say 2, and click OK. So this shows the reaction forces. You have 13 kilonewton and 6 kilonewton as the horizontal force. Now let's see what values we get from the hand calculations. I'll go back to the PDF and see from the hand calculation what values we are getting. Okay, so we have a 6 kilonewton horizontal load applied. That means we'll have a horizontal reaction here at support A, and a total vertical load of 21 kilonewtons applied. So we are getting HA as minus 6 kilonewton, minus because it's in the negative X direction, and VA is 13 kilonewton and VG is 8 kilonewtons, which is exactly same as the reactions that we are getting in the software. Let us now look at the forces, the member forces, compression or tension in the structure. So we go to results, forces, beam forces and moments. Okay, and for the axial forces in the members, since we not have any moments, we won't be looking at the moment diagram My. We'll look at axial force diagram, which is Fx. So axial force is denoted as Fx in the structure. How do we know that it is X, Y or Z? That is determined by the local axis of the element. So each element in the model has its own axis system, has its own local axis, which is different from the global axis. To display that local axis, we can use this icon which resembles a monitor here. If I click on display and go to element and click on local axis and click OK, you can see that many such small axis systems appear. Now if you closely look, if I turn on the isometric view, and if I zoom in on a particular element, say this particular member, you have X, Y and Z as the local axis. Now X is along the member, always along the member, so it represents the longitudinal axis of the element. That means for any kind of axial force any actual force value that you want to see, you need to select Fx to see the result. Okay, any kind of moments you want to see, bending moment, then My. Okay, any shear force that you want to see for an element, that is Fz. Okay, so that's how we see the we come to know that which type of force resembles which component in the model, in the finite element model. So I will undisplay the local axis and switch on to the front view again. Now I will select Fx and just check this off, absolute maximum check on both I and J. So we want to display the values of the compressive or tensile forces at both ends of the element, and click apply. So the moment we click apply, we get the values of the actual forces. Let me switch back to the absolute max so that we get a single value for maximum value for every member, and maybe change the number of decimal points to 2. Okay, so this one will give you more accurate, up to 2 decimal places. Okay, so we are interested in all the members on the right side, all these members. So we can see that some values are negative and some are positive. What does it mean? So the negative values are the values that are in compression, and the positive values are the forces that are in tension. So everywhere you see this is 18 kilonewton in tension, this is 8.49 kilonewtons in tension, 8.25 kilonewton in compression, 11.31 kilonewton in compression. So these are the actual forces, the member forces in the structure. Let's see what forces we actually get from hand calculations. So we go back, and these are the different ways you can calculate it using hand calculations, namely the method of sections and the method of joints can be used. You can have an equilibrium by cutting a section and drawing a free body diagram, or you can look at a particular joint and see what are the forces, summation of forces on that joint. Here are the results. So theoretical results you have here, and they are matching exactly with the software results. So we can say that the model is correct and we have considered all the assumptions correctly. So this concludes our this tutorial number 2 session, and to find out or to get access to all the material, the document for this particular tutorial, you can look at the link in the description. And to know more about the different types of analysis like frame analysis and buckling analysis in the finite element software, stay tuned to our YouTube channel MIDAS UK, and this especially the MIDAS Gen tutorials page channel, where you can find out all these simple tutorials with hand calculations. That's it for now. Thank you.